This is the first in a series of video-based lessons that will introduce the basic optimization concepts and use optimization in context of business problem solving in the areas of production, logistics, and scheduling, to name a few. In addition to the simple optimization problem covered in the videos, there will be several in-class optimization exercises to reinforce these concepts and provide hands-on experience with optimization modeling. This material is covered in Chapter 13 of our textbook. We begin by emphasizing that in addition to simulation models, optimization models provide the foundation of prescriptive analytics, which also includes a variety of other methodologies from game theory to decision analysis methods. The overall emphasis here is moving from descriptive and prescriptive analytics to prescribing what to do in a particular situation. That is, recommending the course of action that will result in a more efficient use of resources and optimal system performance. We next define optimization as the process of selecting values of decision variables that minimize or maximize some quantity of interest. This is where the word prescriptive comes into play. The optimal values of the decision variables are the prescription about what to do in a given situation. The few business problems described on this slide can be formulated in part as optimization models. Scheduling a fleet of vehicles to pick up products at warehouse locations and deliver them to the customers in a way that the overall cost of the operation is minimized is a non-trivial problem. The resulting schedule is the prescription on exactly what to do. That is, which vehicle will go from which warehouse to which customer along which route in such a way that all the pickups and deliveries get done within the required time windows and at the lowest cost in terms of labor, gasoline consumption, and miles traveled. Making a selection of investments and deciding how much to invest in each in order to meet the required rate of return with minimal risk is a general description of portfolio optimization problem. Here again, the resulting list of investments together with the investment amount is the prescription on exactly what to do. That is, which investments to select and how much to invest in each, so that the expected rate of return is realized at the minimum possible risk taken. Finally, finding the best set of advertising media to buy into, how much to allocate for each, so that the overall advertising budget does not exceed a prescribed amount, is another example of an optimization model. Different advertising media, both within and across different media types, leave different impressions on customers we are trying to reach. Generally, the response curve is S-shaped with slow start, rapid buildup, and then tapering off in the number of customer impressions. The independent variable in these relationships is time and or money, with dependent variable representing impressions or actual sales. Here again, the resulting list of media outlets, together with the amounts to be spent on ads with those outlets, is the prescription on exactly what to do. That is, which media types and outlets to select, how much to spend on advertising on each, and for how long, while staying under the overall advertising budget constraint and maximizing the expected customer impressions or sales. One of the earliest types of optimization models, developed during WW2 to aid with logistics in multiple theaters of operation, is the so-called linear programming model. The word programming is not used here in a computer programming sense, although the algorithms used to solve linear and other optimization problems are most definitely programmed into a number of enterprise planning, financial, and other software systems today. As a matter of fact, without computers, these algorithms would be too difficult to solve, or impossible to solve, I should say. We will use the term or the terms linear programming and linear optimization interchangeably. It is much more important to understand the concept, so we will not worry too much about the name. I will get to the word linear momentarily. The decision variables are the unknown values the model is trying to determine. These are the prescriptions on what to do, as we will refer to it in this class. One of the basic examples is the production mix, and the decision variables represent the number of units of each product we should produce. The objective function is the quantity we want to either minimize, think about cost, or maximize, think profit. So in our production mix example, we want to decide how many of each of the products to produce in order to maximize the total weekly profit. The constraints limitations, requirements, or restrictions imposed on our decisions. We can't decide to produce an unreasonable amount of each product in an effort to make our profits huge. To do so will simply not be possible because there are material and labor constraints, among others. The total amount of labor and material used cannot exceed the total amount of labor and material that is available for that week. Now back to the word linear from linear programming or linear optimization. If the objective function and all the constraints are linear functions of decision variables, and this is not always the case, then we have ourselves an LP or linear programming model. In addition, all the variables are assumed to be continuous and non-negative, which simplifies the solution methodology and analysis. Our production mix model is linear because the profit equation, our objective, as well as both labor and material constraints are all linear functions of production decision variables, as you'll see on the next slide. A more generic and more mathematical formulation uses X for the decision vector. So for two products, X is x1, x2, a pair of numbers, where x1 represents the number of units of product 1, or pounds, a quantity of product 1 to produce, where x2 means the same thing for product 2. C is the marginal profit vector. C is C1, C2. So another pair of numbers where C1 is the marginal profit from producing a unit of product 1 or a pound of product 1, and the same goes for the other product. Matrix capital A here, the availability matrix, or the marginal labor / marginal material matrix in our example. So for two products, this is a 2 times 2 or 2 by 2 matrix. Each of the four elements is either marginal labor or marginal material requirement for a single unit of the appropriate product 1 or product 2. Finally, at the very bottom, B is the material and labor availability vector. B equals B1, B2, where B1 is total number of labor hours available and B2 is total number of material, raw material in pounds that can be used. Let's continue with our simple product mix example by providing the actual data for the marginal profits, labor and material, as well as the labor and material availability in the current week. First, note again that X1 represents the number of pounds of drug 1 we want to produce, with X2 representing the same for drug 2. The management knows drug 1 marginal profit is $2 per unit right here, with $3 per unit for drug 2. Manufacturing knows it takes 4 hours right here to produce a unit, or a pound I should say, of drug 1, with 3 hours for producing a pound of drug 2. The total number of labor hours available for producing both drug 1 and drug 2 is 12 hours per week. Operation also knows it takes 1 pound of raw material to produce a pound of drug 1 and 2 pounds of raw material, so twice as much, to produce a pound of drug 2. The total quantity of raw material available is 6 pounds per week. Review briefly the mathematical formulation of the product mix linear program in the top right corner here of the slide. The 2x1 plus 3x2 is our total weekly profit function that we want to maximize. This is subject to labor constraint 4x1 coming from here plus 3x2 less than or equal to 12, which says that the total number of labor hours used, okay, by using 4 hours to produce a pound of drug 1 plus 3 hours to produce a pound of drug 2, okay, cannot exceed 12 hours altogether. The material constraint x1 plus 2x2 less than or equal to 6 says the same thing. You cannot use more material than you have available. Okay. Finally, the amounts produced, x1 and x2, have to be non-negative, which are obvious but still necessary constraints. In the vector matrix formulation towards the bottom right of the slide, so all this as well as that, okay, the marginal profit data for each product belongs to vector C, okay, which is then multiplied by production vector X, okay. Marginal labor / material data to matrix A, which is then multiplied by production vector X. It has to be less than equal to the availability vector B. Okay, so the shorthand notation for the whole thing is max cx subject to ax less than or equal to b for x is greater than or equal to 0. And you'll see that also on the next slide as well. Okay, so before we sort of put this, in practice on a spreadsheet, which is, going to be a little bit more intuitive, hopefully, than the math notation. I'm going to show some graphs as well. Let's open the lect3 underscore lp underscore example Excel file and make sure that the graphical solution, the first tab, is active. Okay, this is a good place to pause.